All right, so one of the theorem, the key theorem that we talk about today is going to ask you to talk about the distance from a point to a line. Okay, the distance from a point to a line. So we need to make sure that we understand that there are actually a lot of distances from a point to a line. Think about where you're sitting as being a point, and think about the wall in front of you as being a line. And we talk about the distance from you to the wall. Are there a lot of different routes that you could take to get to the wall? Yeah. Okay. So when we go from a point to a line, the idea is if I look at this picture here, and we'll go back to that slide so you can write it. If C is my point, frozen. If C is my point and EF is my line, aren't there a lot of different routes I could take to get to that line? That dotted line being one of those routes, that dotted line being another one of those routes, that dotted line being one, right? We've got a lot of different routes. And you see that number EC being the length of the distance from C to that line, right? What is happening to that length right now? Getting shorter. What happens eventually? That length gets longer. So if I'm getting shorter, then eventually I start seeing I'm getting longer and longer and longer. There had to be a place in the middle, right? And that place in the middle is when my distance was the shortest. Okay? Would you agree that 5 was the shortest of the numbers that were up there? Okay? Now I want to talk about why. Okay? Think about this. When we talked earlier in the chapter, I guess it would have been chapter 4. We talked about that triangle right there. What kind of triangle is that? It is isosceles, right? Meaning that these two legs meaning that leg there and that leg there were equal, correct? Okay. Now are both of those legs part of, let's say, one of these blue triangles? Okay. Is that a stuttering problem? Is everybody okay with that? The legs of the isosceles triangle are both hypotenuses of one of those right triangles, correct? Okay. Now, if that's a right triangle, how does that blue distance relate to that red distance right there? Say it again? It's bigger. Hypotenuse has to be bigger than the legs, right? Okay. That red distance is a leg of that right triangle, which means if it's a leg of a right triangle, it is smaller than that hypotenuse. When I bring that in, create that isosceles triangle. Okay? Looking at one kind of branch of that isosceles triangle. Is the hypotenuse of the right triangle on the left longer than that one? Okay? Is it longer still? Okay? But is this one here, where that isosceles triangle right there, is that distance C to G right now smaller than it was when it was out here? Yeah. But what is it approaching? It's approaching that length of 5. Eventually, all of those points are going to be right there, correct? Okay? So the idea is that because those distances that were kind of slanted, okay, that were the hypotenuses of those isosceles triangles, because those are hypotenuses, they got to be longer than that segment CE. So CE then has to be the shortest segment. Does that make sense? So when we talk about a distance from a point to a line, a distance from a point to a line, like we said, there's a lot of them, but the one that we're going to agree on as being the number that we associate with that distance is always going to be the shortest one, or the smallest number. Okay? So when we go from a point to a line, we're always talking about the shortest distance from that point to a line. All right? And then that falls in line with a lot of the other facts that we're interested in. It works well with all the rest of our algebra and our geometry. Okay, so that's a very, very nice thing to have and to understand. Now, the reason we talk about that is because it is the key concept in that theorem right there. Okay, without having that last statement, okay, we can't understand this one. Okay, what? Man, you guys are slow. How long was that up there? It was up there at the beginning of class for 4 minutes. You got it written down, don't you?
I got a question. Are you going to work out?
Yes, I'm going to work
I'm
out.
asking you. Those the
I mean, they're why they're just so I can talk to my computer. So I don't have to yell. No. No. They're Mr. Wilkerson's. He does. That's why he gave these to me. All right, so the distance from a point to a line is the length of the perpendicular segment from the point to the line. Okay? Shortest distance always has to be from a point to a line, always has to be perpendicular. Okay? That's going to be something that plays over time and time again from here to the end of the year. I use it all the time in my college algebra class to prove things with students, to prove relationships, theorems, formulas, that kind of stuff. That's a very, very, very key concept. All right? Still writing. Unbelievable. We got to write faster, guys.
You don't have it written down either. I got a burn already.
What? All right, so we get to this theorem. It says if a point is on the bisector of an angle, the point is on a bisector of an angle, then the point is equidistant from the sides of the angle. All right, now you're going to see here in a moment why we had to talk about that last idea so we can address and understand this idea. Okay? Would you guys agree that the sides of an angle can be extended and or interpreted as lines or rays, right? Okay? Would you agree that a point on the angle bisector, okay? So up here, this point S is a point that is not on one of my sides of my angle, right? The sides of the angle are QP and QR, correct? So that point S, because it's not on one of those sides, we can find the distance from point S to those sides. Well, the distance from point S to those sides has to be found by using perpendicular segments. So that's why you're seeing a right angle at P and a right angle at R, representing then S to P and S to R being the shortest distances from S to those respective sides of the angle. This theorem says those distances have to be the same. Okay? So any point that is on an angle bisector, is equidistant from the sides of the angle. Okay? We're not going to talk you through the converse. The converse is also true, okay? Meaning if I'm finding myself to be equidistant from two sides, two rays of an angle, then that means I must be on the angle bisector of that angle. Okay? We don't use the converse all that often. It does pop up every once in a while, but the angle bisector theorem is more prevalent, more used as we move on. Okay, that's the one I want to target today for the most part. So again, I kind of talked about this last week. My hopes are that you're not writing the full converse of the angle bisector theorem out. Okay, write the angle bisector theorem, and then after that say, asterisk converse is also true. And now because we know how to make converses, we should be able to kind of wrap that statement up in that phrase. Okay, save yourself a little bit of time. Now, that's what we do in class. But if you need to then leave class in this evening, write out that theorem, go ahead and do it. Now, but you have now the tools to remind you how to write that out. If you're a person that says, I need to have the entire theorem in my notes. Okay, so what is it? Let's just kind of walk through and talk through what this is actually saying to us, and hopefully make an understanding of that. Okay. Right now, I've got this angle up there. Okay, just angle. What is that? EAF. Angle EAF. Okay. If I find the angle bisector, would you agree that point D is some point on that angle bisector? Okay. Now I'm going to, just to prove the point to you a little bit, I'm going to remove, well, maybe. I want to remove that ray. There we go. I want to remove that ray. And I want to look at point D. Would you guys agree that point D is a point that is not on the line that remains? Okay. So how do I find the distance from point D to that line? I have to use what kind of segments? Or what's the relationship between the segment D to that line? It has to be what to that line? It has to be perpendicular. Okay? So that distance right there, that is the distance from D to that ray. But that ray is a side of our angle, right? Okay? Now if I do this, where'd that line go? There we go. Would you agree D is now a point not on that ray or that line? So if I want to find the distance from D to that line, I have to find the perpendicular distance, right? Okay? So that perpendicular distance would be that. What the theorem is saying is if I look at those two dotted distances, they should be identical. They should be the same amount. Okay? No matter where D is, as long as it's on the angle bisector. As I start sliding that, now the values obviously change, but what do we argue about the comparison of DE to DF all the time? They're the same. Why? If we look at those two triangles, what do you think the argument is about those two triangles? They're going to be congruent. Okay? Do they, by definition, A to D is an angle bisector, right? Okay? And the theorem says if a point is on the angle bisector. So that means this has to be, AD has to be an angle bisector. So that angle has to be congruent to that angle, right? The way we measure distance from D to those sides is using perpendicular lines. So we know that angle and that angle are both right angles, correct? What segment is in both triangles? Yeah, DA. So now do you have an angle, another angle, and then a side that is non-included, and then down here in the blue one, an angle, another angle, and then a side that is not included? So those two triangles congruent by AAS. And if they're congruent by AAS, we never mentioned the dotted lines, right? Okay, those were sides that we haven't talked about. So by CP, CTC, good. CP, CTC says that those two distances, DE and FD, are always going to be congruent. So it's a very useful fact that, again, is generated or is a conclusion of congruent triangles. Okay? Any point that is on an angle bisector is always equidistant from the sides of the angle. All right? And we're going to use that and see kind of some benefit of that. If I told you right now to look at, let's say, let's say this is the wall in front of you. Let's say this is the wall to the left of you. And I ask you to place yourself in the classroom so that you are equidistant from both walls. Where would you put yourself? You would put yourself on that angle bisector, wouldn't you? Okay, so that would be kind of the, if we look up at that corner up there in the left of the room, okay, you'd be putting yourself on the line from me back to my bookshelf, right? Okay. Hi, Dalton. So Dalton is pretty close to being where he's at right now. He's pretty close to being the same distance from this wall up here as he is from this wall right here. Okay. Now, there are kind of real-life applications of that, okay? If you've ever been to, like, a studio or, like, maybe a building that they conduct, like, plays in, a theater that's been designed just for those types of things, the placement of microphones, the placement of stages, the placement of speakers and all that kind of stuff is important because of the distance that sound has to travel and the distance that sound has to travel to be picked up by microphones and all that kind of stuff, okay? They use math that is aligned with this idea, with distance between walls, okay, or distance like we talked about with circumference the other day. They use these pieces of math to kind of make good decisions about where to place microphones and speakers and that kind of stuff so that the audience is benefited from that stuff. Does that make sense? So it's an enjoyable experience, okay? Have you guys ever been to, now this isn't the current math that we're working on, but you've all been to Washington, D.C., right?
No.
A lot of you go on that trip?
I refuse to go.
Okay. When you go to Washington, D.C., you sat in a room, you stood in a room at one point where somebody stood over here and they whispered. And the person that was standing at B, which might have been hundreds of feet away, could hear you whisper, as if you were whispering in their ear, right? Okay? Right. So that is a feature of reflection of sound, okay, that was used, it was kind of targeted by the architects of that room. They made that room elliptical, and the ceiling was elliptical as well. And basically what happens is that all of our sound, okay, our sound waves that emanate from us, okay, will hit these walls, okay, and bounce back to this other position. And because sound travels at the same rate in the same mediums, all of these distances from A off the wall back to B, all those distances added together should be the same. Okay, so AF plus FB is the same thing as AD plus DB. Okay, and because those distances are the same, all of our sound waves are bouncing off the walls and coming redirected at B at the same time. So it sounds like this person's just in my ear whispering, but I'm hundreds of feet away from them. Does that make sense? So that is a geometric concept that has been harnessed or kind of targeted through the architecture of that building for that purpose. Okay, a lot of times they're called whispering rooms or whispering chambers because of that principle.
Why would you want something like that? Like, what if they scream?
Say it again?
Why would you want something like that? Like, what if they scream? It'll be like right here.
Well, but that only works. So if only I'm standing at B, will that work, right? Or if only I'm standing at A. So if I'm standing at that position right there, even though I'm closer to the person at A than the person at B is, I'm not going to be able to hear the person whispering at A. Okay? So the principle of that, the reason that it's just the architect of that building just said, hey, this is what I want to be able to do. Okay? Or it might just be a maybe in that building, the Capitol building, I believe is where that's at. Maybe that was just a byproduct. Maybe they didn't intentionally do that. But some whispering chambers are intentionally made that way, just for the attraction, just for the targeting of that geometric concept. Yes. Okay. I'm following stuff out. On the white word, yeah. Okay. So what I'm trying to say is the things that we are talking about, guys, are used in architecture. They're used in making decisions to kind of exploit geometric concepts, okay, and how they interact and are usable in the real world. All right, so now that we understand that with one angle, a triangle is simply a grouping of three angles, right? So can I do the same thing for this triangle? Can I find the angle bisectors of this triangle? So I'll find one of those angle bisectors, okay? So let's find bisector 1, okay? When I find that first bisector of angle B there, okay, any point that is on that black ray should be what to the purple sides? Equidistant. That point right there, no matter where I put it, the distance from that point back to this ray and back to that ray, or I guess segments, okay, is always going to be the same. Is that okay with everybody? Okay. If I take that bisector, any point on that bisector is going to be equidistant from the blue sides. Is that okay? Okay. Any point on that third bisector, just hit puberty, that third bisector is going to be equidistant from the two red sides, right? Okay. So let's put all these in there. So they all are what at that point? What do we call them when they all intersect, when three lines intersect at one point? Nope. Starts with a C. Concurrent. Those three lines, those three rays are concurrent at that point. Now, what's the feature? Okay? Well, here's the idea. Okay? Any point, and I could just look at two of the three bisectors. Does that make sense? So those two or those two, do they all intersect at that same point? So we only need to look at two of them. But what we're saying is that that point of concurrency, if it was, okay, like I said, I should put that point of concurrency in here. That point of concurrency is equidistant from the blue lines, right? Okay? And it is also equidistant from the red ones. Well, if I highlight the blue ones and the red ones, it highlights all the segments on my triangle, correct? So if it's equidistant between the red ones, and it's equidistant from the blue ones, then when I highlight all of them, it's equidistant from all three sides of the triangle. So if I had like a triangular room, I told you go find the spot in that room where you are going to be the same distance from all three walls, that's where you would put yourself. You would put yourself at what we call the end center. Okay? So the vocabulary word, end center. It is the point of concurrency for angle bisectors. Point of concurrency for angle bisectors. Say again? Yeah, but it's the point of concurrency for the angle bisectors. Because we have multiple, last week when we talked about the point of concurrency for the angle, the segment bisectors. That was the circumcenter, right? So we're going to have four centers. So we'll have four situations of concurrency. This is the situation for where the angle bisectors are concurrent.
So then what's the point of concurrency? I thought it was when you add it, when you take the lines.
Yeah, the point. So point of concurrency is just where any three lines intersect.
Oh, so it can be like some random spot on AC going down. AC.
Yeah, if I just have, some random segments or lines like those are concurrent at that point right there, okay? But with talking about special types of lines like these angle bisectors, we just call the incenter the point of concurrency for or of the angle bisectors. Okay, so that's a nice thing. That is a nice center to have. Now, it's called an incenter, okay? It's called an incenter. Now, I want you to kind of make the connection here. Right now, what kind of triangle do you think we have here? That's obtuse. 126-degree angle. Where is the incenter? On the inside of the triangle, okay? When I look at this triangle, what kind of triangle is that? A right triangle. Where is the incenter? So on the inside, okay? What kind of triangle is that? It's acute based off the angles, right? Okay. If it's acute, where is the incenter? On the inside. How does the prefix in remind me where the incenter is? It's always on the inside, right? Okay. Because the angle bisectors always will intersect on the inside of your triangle. Okay. No matter what triangle you have. All right. So that's nice. The purpose of this, okay? We said that the incenter is going to be the point that is equidistant from all three sides of the triangle, correct? Now, I'm interested in finding that distance. So I'm going to find I to G, okay? Basically, the idea is, would you guys agree if this is a point? Would this be a line or a segment that point is not on? So can I find a distance from there to AB? But it has to be what to AB? Has to be perpendicular. If I find that angle, it's perpendicular, right? Okay. Can I do the same thing from I to H? Okay. So I'm calling I the incenter. If I go from I to H, okay, to find that distance, it has to be what to AC? Perpendicular. So if I find that angle, it is perpendicular. And what is the third side that we have not gone to yet? B to C, right? So if I find that distance, find that angle, would you agree that's the right angle? Okay, what showed up with all three of these blue segments? They were all what? 1.33. That should make sense to us, right? 1.33, we said it had to be equidistant from all three sides. Right now we're just seeing that the distance from the incenter to each side is 1.33 units. All right, so let's do this. Let's take a segment of length I to H, okay? And let's rotate that segment. And I don't want that one, I want the purple one, so give me a second. Purple one. I want to rotate it around the incenter. And what's going to happen when we do that? What's H prime? It's creating a circle. Okay? If I were to trace that, okay, we get that circle. Is that okay with everybody? Okay, that circle, where is it drawn in respect to my triangle? Inside it, right? Okay, so the prefix in telling me inside, correct?
Yeah.
Now, when we draw something or write something, what's the word that we use for that? Scribe, right? Okay, so that is referred to as the inscribed circle. Okay, every single triangle you come across is going to have an inscribed circle. Okay, so that is the inscribed circle. In the center of that inscribed circle is the in-center. I know I got a lot of things going on here. Let me clean it up a little bit. All right, so every single triangle has an inscribed circle, okay? That circle, its center, is going to be the in-center, and its radius is the distance from the in-center to a side of your triangle, okay? Now, I've got one more question to ask you. Actually, I got two questions to ask you. First one, if I were to just show you that information there, and just looking at the circle and that line AB, okay? How many times does the circle touch line AB, or how many times does line AB touch the circle? Just one time, right at G, correct? Okay. Does anybody know the mathematical word that we use to describe when a curve and a line, and it actually could be two curves, or just when two objects just kind of bump each other like this? It's not the word intersect, because it's a special type of intersection in which this happens. It starts with a T. Okay, what does, go back to Mr. Stoddard's class. He gives you a vocabulary word. He gives you a synonym for the word able to touch. What's that mean? What's a word for that? It starts with T. T-A-N.
Tangible.
Tangible. Okay? So tangible means to be able to touch, right? So tangible means able to touch. So in math, when I have a line that is touching a circle one time, we say it's what, Lucas? What did you say first? You said tangent, right? Okay. So that line, BA, is tangent to the circle, or the circle is tangent to the line. When you hear me say, I'm going to say this all year long now, okay? When two things are tangent, they're touching at one point, okay? And usually we talk about, especially in this class, and really only in this class, we're going to talk about circles and lines, okay? When a circle touches a line one time, it's tangent. When we get into pre-calculus, we get into calculus, we'll start talking about parabolas touching lines, we'll talk about cubics touching lines, and talk about them being tangent together that way. We can also talk about circles. If you take two dinner plates, slide them together. How many times do they touch? Just once, right? That point where they touch is the point of tangency. When I say intersection, so the idea with an intersection is, that's a good question. So when we talk about like shapes that intersect, we're usually talking about the fact that right there, if I have that line and that ellipse intersecting, that we kind of pass over from one side of the line to the other side of the line, okay? Meaning that my ellipse is kind of on both sides of the line now, where if I was going to be tangent, we would have kind of a situation like that, where now you see how the ellipse is all on one side of the line. So intersect kind of means they overlap each other. They continue on a lot. I guess the best way to describe it is when I take this line, that line creates two planes. Okay, we call them half planes. It essentially creates that region there. Would you agree with that? And it also creates then, let's talk about this top one. Okay, so the line creates two half planes, right? We've got a like maroon plane on the bottom and a blue plane on the top. When we intersect, basically it means that your circle or your ellipse, your curve, is now in, part of it's in both planes, okay? But if they're tangent, then we see how the ellipse is only in one of those half planes, okay? So that's kind of a way of thinking about that. So tangency is a kind of special case scenario for intersection. Does that make sense? So it's a more kind of informative way of how things intersect. So why do we talk about that? If I look at this here, to be inscribed, you have to be tangent to all three sides of the triangle. Okay? Meaning that I touch each side of the triangle only one time. Therefore, if I were to give you this picture, we agree that's a triangle, correct? We agree that that is a circle, correct? And if I move it, would we agree that circle is on the inside? Is it an inscribed circle, though? No, because R is not the in-center of that triangle, right? Therefore, that circle on the inside is not tangent to all three sides. So when I say inscribed, and I'm giving you this way of inscribed means inside, right? That's not the only requirement needed. There's some geometry requirements, and the geometry requirements is that the sides have to be tangent to the circle. All three sides have to be tangent to the circle. I could take any circle and kind of do this with it, can't I? Can I take that circle and make it tangent to two sides? Okay, but I can't make it. I can't make any circle tangent to all three sides. It only has one circle that will be tangent to all three sides. Huh? Yeah. If I start to increase this size, I'll eventually be able to find that one, and then locate. But the size of that is dictated by where the in-center is, because it's the side or the distance from the in-center perpendicular to a side of the triangle. All right. So here's my question. Last question. We'll be done. If I have that triangle right there, oops, that triangle right there, what is, I find the perpendicular bisectors, what did we call that point, what did we call that point right there last week? Circumcenter. So point D, I'm going to rename as the circumcenter. Okay, and today then we're talking about, not that. No. Okay, so we're talking about that point right there, which is the intersection of the angle bisectors. Okay, so this point here is referred to as the in-center, right? Now the question is, are they the same point? No, obviously for this one they're not, right? Do you think that maybe eventually they will be? Okay, so now I'm going to, it's just going to be, let's see if I can do it this way. All right, that's pretty close, right? Okay. What kind of triangle do you think that is? Equilateral. Okay. If I look at the angles, they're all pretty close to 60, right? So right now, the idea is that because they're not all 60, if I were to zoom in, those 2 points do have a gap between them, right? Okay. So they are not 100% the same point right now, but they will be. Okay. Why does that make sense for an equilateral triangle? Why does that work? Why does the circumcenter end up being the same thing as the in-center? What do you know in an isosceles triangle? What do you know about that segment compared to that segment in an isosceles triangle? Okay, they're congruent. Okay, so then in an isosceles triangle, remember when we bisected this angle? When I found the angle bisector, the vertex angle, what was the relationship that existed down there at the bottom where my cursor was? Okay, so it went through the midpoint, right? And it was what? 90 degrees. So that blue line, okay, A to wherever my cursor is, that was a perpendicular bisector of that base on the bottom, right? But wasn't it also, by definition, the angle bisector, the vertex angle? So do you have a segment there that is an angle bisector and it's a perpendicular bisector in that triangle? Does that make sense to everybody? Then, we also, if this is equilateral, isn't that segment, which I'll make purple, and that segment, aren't they congruent? So can I call this a vertex angle? And find the find the angle bisector of that, so make that 30, make that 30. Wouldn't this be the base then? And when we take the angle bisector of a vertex angle, it's got to be perpendicular to the base, at the base's midpoint. So that segment is also an angle bisector and a perpendicular bisector at the same time. Is that all right? Equilateral triangles are the only triangles in which all three angle bisectors are also all three perpendicular bisectors. Is that okay? And it's all because of the corollary that said, if you take an angle bisector of the vertex angle, it is in perpendicular to the base at the base's midpoint. Okay? So these are features that we have to be able to kind of understand and interpret because we're going to use them consistently throughout the year. Okay? So the end-center, equidistant from all three sides. Circumcenter, equidistant from all three vertices. Okay? Those might be two phrases you want to write down. Circumcenter, equidistant from all three vertices. End center, equidistant from all three sides. And then in equilateral triangles, they can be the same point. Okay? Those are kind of recognition type questions or understanding type questions I'm going to ask on tests and quizzes. Okay? I might ask you, always, sometimes, never, the end center and circumcenter are the same point. You would say sometimes, right? Okay. Most of the time they're not, but in an equilateral triangle, that's the one time that they are the same. All right. There is an assignment on Math Excel. It is